Okay, welcome to discussion. Again, if you have any questions, feel free to ask them. And if it's something I need to work out, I can do that on the screen for you. If you have any questions like that, again, you could type your questions in here, either to everybody or just to me. Again, I'll be here till about our regular time to answer any questions that you may have on anything we've been talking about in terms of chemistry. Not all general questions, but in terms of chemistry. If you do have questions, just again, feel free to type it in and I'll try to get everybody's questions answered. Yeah, I did get an update from her last week when I did get some questions about the grade. So she did send me an updated one, which I imagine would cover, before last week and this week and stuff like that. I just truthfully, unfortunately, haven't had enough time to kind of update everything. So my goal is to take those and try to update with it, with what she gave me, which was, again, I think I got it in the middle of last week, sort of an updated one with any type of corrections I guess you guys made, and she maybe gave some corrected points and stuff for certain labs. So um, I do have that from last week. I just haven't had an opportunity yet to sort of upload it or do all the grades together. You're welcome. Like I said, my goal is maybe to get it up there by this weekend sometime. Okay, no problem. We keep work on it. If you have a question, that's what I'm here for. So feel free to ask if anybody has a question on anything. I'll hang out. I haven't looked at it recently. But last time I looked, there was a number of people that were watching the recordings, and I haven't actually looked recently in terms of the other. Do you have a question on worksheet 6? I don't have it in front of me. If you could just kind of type in sort of what the question might be, I could probably answer it. Okay, so it's a gas law. That would be one of the chapters that was in that group I was trying to think of. All right, so let's take a look here. Let me just get a fresh sort of screen here. So we'll take a look at it here. So um, we have a volume that's 27.5 liters. Oxygen gas and a temperature that's 25 degrees Celsius, and that ATM is a pressure of 1.05. And if the gas is then cooled to another temperature of 40 degrees Celsius, while the pressures increase to 2 atmospheres, we are looking for the new volume. So again, as we talked about with sort of these gas law problems, oftentimes it's good to sort of write out everything. And there's a couple ways you could solve this one, but one way you could use that has all those sort of variables in it is the combined gas law, and that's P1 V1 over T1 equals P2 over T2. And the only thing that we don't have to do, so I will use something aside and T2 would there, P2 would end up, and leave us P1 over T2. So we get all the information into here in terms of our pressures. They're both in atmospheres. But much like every gas law, we do have to convert our temperature into Kelvin. So the temperature in Celsius plus 273 will give us our temperature in Kelvin. So I'll just write it over here. Our T1 then would be 25 plus 273 to convert that into Kelvin. And I'll grab a handy dandy calculator here just to make sure. So 25, and I still punched it in wrong. Let's try that again. 25 plus a 273, and gets us a 298 Kelvin for that guy. And then for our T2, it would be 40 plus 273. And that would get us, if I actually hit the right buttons here on the calculator, three. Remember, always got to be all right. Our D was 3.5. T2 by 12 is 8. And our T2 is 2. So the cancel the volume. So if we put all that in, 1.05 times 27.5 times 313, it equals, divided by 298, it equals, divided by 2. It looks like we end up with what you got there, which is 15. Does that make sense? Questions on that? So a couple of things sometimes people will oftentimes do on these sort of gas problems that sort of they forget to do is they'll use it in Celsius instead of convert it to Kelvin, and then the rearranging part of the equation here oftentimes is problematic for people. So remember that, again, as we talked about in class, if you're moving something from one side, it pretty much any application is a good way to sort of remember how to move things around. Any questions on that? And also, it's a good thing to remind as well. And I think in the book, there may be some questions like this where they will give you some temperatures in the gas law, and they'll ask for a temperature to be found in Celsius, and they'll give you the temperature in Celsius. Remember that when you use a gas law, even if you're given the number in Celsius for the temperature and you got to calculate the temperature in Celsius, you still have to convert it into Kelvin and then put it into the gas law and then convert it out of Kelvin when you're done. Any questions on that one? You're welcome. Sure. Again, I apologize. It's just hard to, I don't really have it in front of me. So if you could just, like you did before, kind of type in the information, it'd be great. Or, if you want, I could release your microphone and you can tell me if you want. But if you want to type it in, that's good too. Yeah, so just go ahead and type in the, you don't have to type it word for word, but just kind of the important numbers would be perfect. Okay, so we got a gas occupies 35 milliliters at 21 degrees Celsius. What is it at STP? Let me just scroll to a new screen so I got some fresh places to write. Okay, so this one also you could actually solve a couple different ways. So we'll talk about a couple different ways you could get to the answer on this one. Again, if you just kind of pull out the information like we talked about in class, we have a volume that is obviously 35 milliliters. We have a temperature that is 21 degrees Celsius, and we have a pressure at 745 torr. And we're really looking for the volume at STP. So remember that STP stands for standard temperature and pressure. And when they do give you STP, it actually does have values. The temperature is 273 Kelvin, and the pressure is 1 atmosphere, or it could also be, in certain situations, you could think of it as 760 torr or 760 millimeters of mercury. So remember, they're all the same in terms of that 760 meter. You also have what you cases that same 64. If you set numbers, you saw this from back ways we really make them by over one. You and P was the name earlier. Actually, you have to compare next to it to convert it to Kelvin. So that's going to give us 273 plus a 21. It's a 290. Yeah, it will also 64 our T was 290 and our E2 would be 700. It's not different than previous one is milliliters. So when we do solve for V2, like we'll do right now, it is going to be in milliliters. So that's 750. I wrote it backwards on 745 was your answer there. Sorry about that. 745. There you go. 745 times 35 times 273 divided by 294 and then divided by 760. That gives us a volume of 31.9 milliliters. And again, it would be milliliters here because this is milliliters. This much all even really comes on. And over here, we'll use people's RT. And you can use the ideal gas law because originally you have a temperature and that is 4. That you remember that is most restricted factors. Could be associated with R and not hit the wrong button. You can look at our and what else has to be. Look at what we have here. So that we don't have is and. So you solve that is and we would want it in the proper use. So if we use this, so 700 by 4 will give us an ATM value of 0.980. So this would be 0.980 atmospheres. Converted and we're basically just moving the decimal point 3 places to the left, and that would get us 0. And that's what and which we converted up. All these will cancel helps, and what you will get is 0.98 times 0.035 divided by 0.08206 and divided by 294. That gives you this number here, which is 0.00142 moles. And you may say to yourself, that's moles. That's not really what we're looking for, which is a volume. This is where we can use a relationship that hopefully you remember, but even if you don't remember, be okay. When we are at STP, 1 mole of any gas will equal 22.414 liters. So again, you can use this conversion factor, but it does have to be at STP. And if we did that, we would take 1 mole is 22.414 liters. The moles would cancel. So if we multiply by 22.414, gives us 0.0319 liters. And again, 1 liter is 1,000 milliliters. And that will get us to 31.9 milliliters as well. So this problem as well, and maybe a good review of some of the gas laws that we were talking about before, actually could be solved both ways. You can either solve it probably a little bit easier and a little bit quicker doing it the first way with the combined gas law. But you also could use the ideal gas law and that relationship of 1 mole is 22.414 liters because it is at STP. Any questions on any of those? Again, you can see you do end up with the exact same answer regardless of which way you end up solving that one. Any questions on that? It is, as you can see, the first way is a lot quicker. Yeah, so the first way you get the same answer, but again, it just reminds you how you can use the ideal gas law, and also sometimes if you forget, say the first way, you can at least try it the second way. So a lot of times with gas laws, there's always maybe a couple different ways you could get to the answer. But if I had to choose, I'd probably do it the first way, since it's obviously less steps and less places where you can make an error. Sure. What's your question? Sure. Just that type of information. I'll be happy to answer it. Okay. Calculate the molarity of each of the following. Okay. Let me just get a fresh piece of screen, I guess. Okay. So we want to calculate the molarity. And if you're out for the night, have a good night. We want to calculate the molarity, which is moles per liter. And we have, it's 521 grams. Yeah. Magnesium chloride. So you want to make sure you get the right formula, which looks like that. And that's dissolved in 4.25 liters to make a 4.25 liter solution. So this is, again, moles of solute over liters of solution. So we really do have the bottom part already. And the top part, which is moles of solute, we don't have, but we do have the grams. So remember, the way we go from grams to moles is the molar mass. And we would need to get that from the periodic table. So hanging out. So we have one magnesium, and again, the key to this is to make sure. So magnesium is 31 molar mass in the periodic table, which is 45 grams. And again, I'm just coming from the periodic table. And again, usually we just take 4 significant figures. So if we add all that together, we will end up with a molar mass of 95.21. And when we do take the numbers off the periodic table for molar mass, and when we calculate the molar mass, reminder, for significantly. So I'm going to cancel. We'll take 521 divided by 95.21, and we will get 5.47 of the hot that we need to calculate the molarity. So really, at this point, we just need to put those numbers in. So the molarity was that, and we would end up with a molarity of 1.29. And you use mole here, moles per liter. qualitatively bands for molar as well. Any questions on those steps? And that's a very common thing you have to do with molarity. A lot of times you're given the solute in grams. So again, using the molar mass from the periodic table will allow you to convert from grams to moles. Any questions on that? Cool. All right, so we're getting towards the end here. Discussion. If you have any more questions, I'll be happy to answer. If not, I'm good. If you're good, have a good weekend. But if you still have a question, I'll be happy to stay and answer. Just let me know. Okay, go ahead. Okay, so let me clear the screen here and get something else to scribble on. And change the color just to mix it up. We'll go with blue. All right, so we're looking for milliequivalents per liter in each of the ion pairs. So remember that basically equivalents are found from the charge. So if something has a +2 charge, what that means is in every 1 mole, whatever you're dealing with there would give you 2 equivalents. And remember that when we go from equivalents to milliequivalents, that is sort of the same conversion as like going from liters to milliliters, right? And there's 1,000 milliliters in 1 liter, which means that there would be 1,000 milliequivalents in an equivalent. So those are 2 sort of important kind of conversions that we use for this. The other important thing is when we look at the formula of Na2SO4, when it breaks apart, it will break apart into 2 sodium ions and then it will break into 1 sulfate ion. And remember when we talk about polarity, if we know everything here is 2 relationship of the whole thing just as it's a relationship. So how change polarity is polarity of sodium ions would be 2 times 0.55 and give us a concentration for the sodium of 0.51, it looks like. So 0.510. When we look at this, so when the slave term liquids that we can get, we look at because we want that near mole we would have we do think this whole thing I do, then minus the automatic effect equivalent, it's just actually the mole state will be 2. And so we have not everything is just so like so that's the mole, but it's only over and we're using sort of a diversion factor. So we need to get to milliequivalents. So nothing has to change in terms of the bottom. We just convert the which is moles into equivalents and go to milliequivalent. But using the ratio of this, we see that 1 sodium and so we have 1 0 equivalents and the change by anything by sodium. We're looking for not milliequivalents, that's so and there's 1,000 milliequivalents. So cancel. And we're going to basically take that number and multiply it by 1,000, and we will get 510 comes out there. Now we want to do exactly for this one, and we and again use so as we saw very middle space went to this point we had 0.0 and use 1,000 now you may notice a couple of things they're the same so are the same, and that's one way that you could check yourself when you do these type of calculations is if you have an ionic compound like what we started with over here, the Na2SO4, because when we put an ionic compound together, if you remember, we balance the positive and negative charges, which means when we look at their concentrations in terms of equivalents per liter or milliequivalents per liter, they always should end up the same. And that's because all ionic compounds basically balance each other out in terms of their charge, which means since equivalents and milliequivalents per liter are really based on the charge of those ions floating around, everything should be balanced. So whenever you calculate the equivalents per liter or milliequivalents per liter for the positive ion and the negative ion in an ionic compound, they should always end up the same answer. Any questions on any of those steps there? Good, good. Any other questions for anybody I can answer? You're welcome. Okay. Have a good night. And then if there's no other questions, I'll probably end this then. Thank you. You have a nice night too. And a good weekend. Have a good day.